A dazzling display of northern lights spotted over North Georgia Tuesday evening, and we may not be fully done with seeing the northern lights in parts of the southeast. Joining me now to talk about this and the implications of these stronger geomagnetic storms is Dr. Piet Martens, professor of solar physics at Georgia State University. Thank you so much, Dr. Martens, for joining me today.
Thank you for asking me.
So Dr. Martens, let me start with this. I mean, we're in a really active phase of the sun's solar cycle. Can you explain what happens when we have these displays of northern lights or the aurora borealis? What is coming from the sun that's actually causing those to happen?
Okay, well, the sun has an 11-year cycle in magnetic fields, so you see sunspots go up and down in a cycle of 11 years, and we're at the max now. And when you're at the maximum of magnetic activity, there are a lot of eruptions from the sun, coronal mass ejections, we call them. And they happen all the time, and sometimes there's one that is directly going to the Earth. A coronal mass ejection is a blob of plasma and magnetic field that's thrown out at 1% of the velocity of light. It's really fast. It gets to the Earth in about a day and a half if it's fast, and then it impacts on the magnetosphere, the magnetic field of our Earth. So it bumps into it and deforms the magnetic field of the Earth. And when that happens, you generate electric fields. That's the same thing as what happens in the alternator of your car. You make it move when you drive. That generates an electric field that generates currents that recharge your battery. It's very, very much the same, really. Here. And those electric fields accelerate electrons that precipitate in the Earth's atmosphere in the regions where the atmosphere is open to the solar magnetic field. And that's near the North Magnetic Pole and the South Magnetic Pole. And the North Magnetic Pole is located somewhere in the north of Canada, not exactly at our North Pole. So around there, you get high energy particles precipitating in the atmosphere, and they generate light. Blue light, red light, and green light. And when there's a large coronal mass ejection that really bumps hard into the magnetic field of the Earth, the region where these high energy electrons precipitate gets bigger. Sometimes it gets big enough to get to Atlanta. And that's when you get auroras in the Atlanta. So these high energy particles cause the lights that you see. And normally it's just located around the magnetic pole in the north of Canada. And sometimes when it's very strong, it goes all the way to the south of the United States. And there is one really famous example, 1857, when the aurora was so bright that people in New York could read the newspaper at night without streetlights.
So when we have these coronal mass ejections coming towards Earth, if you had to put it in like 30 seconds to a kindergartner,
all right.
Why do we get the lights? Why do we get the northern lights, the aurora borealis? What is happening there?
So the coronal mass ejection bumps into the magnetic field of the Earth, deforms it, and that leads to acceleration of particles that hit our atmosphere, ionize oxygen and nitrogen, and when that ionization goes back to its rest phase, these ions emit light. And it could be green light, blue light, or red light, depending on the ion. And that's what you see. The light emitted from ions that have been energized by the coronal mass ejection.
Now, a lot of the photos that we were getting in Tuesday evening were mostly the red light. We got a few of green from here in North Georgia. Can you explain the difference in either what the elements are that they're reacting with or what the height is of seeing those different colors? Is there a difference, red versus green?
There is. The red comes from the highest level in the atmosphere, and it's ionized oxygen. And then the green is also oxygen, but at a lower level in the atmosphere. So it emits at a slightly different wavelength, which is the green light that you see. And then the blue, which you probably haven't seen, but you can see in other places, is nitrogen, which is even lower in the atmosphere. So it depends on how far those energetic particles, these electrons, penetrate into the atmosphere.
And so we also know that from the Space Weather Prediction Center, there's the possibility of more plasma reaching the Earth with the CME today. So is it a possibility
Correct.
that KP index could get up close to an 8 and provide more northern lights tonight?
Yes, that's possible and even likely. There's a sort of what they call a Cannibal CME. It was emitted from the sun, and it's catching up with the first CME that caused the northern lights yesterday. And it's called a cannibal because it will eat it up and make it even stronger. So there's a good chance that the northern lights will even be stronger tonight.
Ah, well, I'm so glad that you explained it. So that means, is that one traveling faster than the original CME?
Yes, typically the stronger ones are traveling faster so they can catch up with the ones that go before it. Yeah.
Now, I know in this active phase of the solar cycle, last year and this year, we've seen several of these much more strong geomagnetic storms impact the Earth. What we haven't heard a lot of, though, are negative implications from those. I know we had the G5 last year in May, and we kind of
right.
luckily got by without many impacts. When we get these stronger G4s or G5s, what can happen to satellites, astronauts in space? You know, is there any implication for people flying on a transatlantic flight? What do we need to be worried about tonight from a science perspective?
So this is actually exactly the research that my group and I are doing at Georgia State University, and that we are supported by NASA and by the NSF to do this, because there are negative implications. One of them is you get more radiation in aircraft on transpolar flights. So if you fly from Shanghai to New York, you go pretty much over the pole, and you can get high radiation doses. And if you get that a couple of times, which like the pilots could have, then that could cause cancer. That's bad. In the future, when we go back to the moon, the radiation from those events also could potentially even kill astronauts. So you want to have warnings in advance so they can seek shelter. So typically the spacecraft, the skin of that is thick enough to reduce the radiation significantly. It can also knock out satellites that have very sensitive equipment. It can, and in the worst case, it can knock out our power grid, which is something we should really be concerned about, of course. And when you get warnings in advance, you can take measures, just like you can take warnings when you have, when you take measures when you have a warning of a hurricane coming in.
So how do you measure that? How are you doing your research? Are you studying past events? Are you looking at different mitigation methods? What's your thesis? What are you really trying to get a hold of here in your research?
We definitely look at past events, as much events as we can collect, which are mostly observed by spacecraft, satellites, over the last 30 years. So you get an enormous amount of data. Those data we try to analyze by using machine learning, which is part of artificial intelligence, and that's why we work closely with our computer science department. So through machine learning, we see patterns. Once we know the patterns, we can apply them to forecast future events.
Wow. So your research might be connected one day to the Space Weather Prediction Center and NOAA, not just what's happening with astronauts on the moon, perhaps.
Oh, yeah, absolutely. Yeah, definitely. We work closely with NASA's Space Radiation Analysis Group in Houston, which does the forecasting for outer space, for spacecraft and astronauts.
When we see these more active phases of the sun, when they are producing these coronal mass ejections and we're getting these northern lights that are happening as far south as southeast, what do you hope people take away from that as just regular citizens?
Oh, that's a good question. Well, first of all, it's beautiful, right? It's just interesting to look at. And people travel all the way to Scandinavia to see that, and to the north of Canada. And now the influence of the sun is real. This is what it can do. And this is a very positive result mostly, but there are also potential dangers from space weather.
And on the flip side, though, they are beautiful. And so if people want to take or try to capture Northern Lights photos tonight, if we end up seeing them come out, what's the easiest way for people to see them? What do they need to know, the basics of spotting it and capturing a picture?
Oh, I'm I'm no expert on taking pictures, but well, you have to look north and get an unobstructed view, of course, and you hope for a clear evening, and then you will see it. I saw it here last night in Montana. You can take pictures with your cell phone camera, even will get the right result. But it's, of course, much better to have a very good camera.
And a little bit of patience, or you get a lot of luck when you just see one of those outbursts for a good 10 minutes.
No, yeah, they last for a while, so, and they come one after the other. So when it's there, somebody calls you up, there's Northern Lights, you have the time to go and look for it.
Excellent. Well, we are crossing our fingers that more folks that didn't get to see them on Tuesday night will get to see them Wednesday evening in those North Georgia skies. Dr. Piet Martens, professor of solar physics at Georgia State University, thank you so much for your time today.
Thank you for having me.